What if I told you that there's a giant rogue planet in our galaxy traveling through total darkness, completely alone with no star to orbit? Scientists are calling this the discovery of the decade, and for the first time in history, they actually measured both how far away it is and how much it weighs. The planet has a pretty ridiculous name. Well, actually three names. Scientists are calling it KMT 2024 BLG 0792, though some call it OGLE 2024 BLG 0516, and others call it Gaia 24 CDN. Three different names because three different telescope networks spotted it simultaneously. The planet weighs about 70 times the mass of planet Earth. For comparison, Saturn weighs about 95 Earth masses. This is an absolute gas giant, a huge ball of hydrogen and helium roughly 10 times wider than Earth. Now, let me explain how scientists even find these things because the method is pretty fascinating. The challenge with finding rogue planets is that they produce almost no light. They are not like stars that burn bright, and they do not reflect light from a nearby sun like normal planets do. Rogue planets are cold, dark chunks of matter moving through space in total blackness. Most are probably colder than 200 degrees C. No light coming off them, no heat signatures, nothing for telescopes to detect. You cannot just point a telescope at empty space and spot one of these things. So, how do you find something you cannot see? Well, the answer is gravitational microlensing. This technique does not rely on detecting the planet itself, it relies on gravity bending light. Albert Einstein discovered something weird about the universe over 100 years ago. He figured out that gravity actually bends light. Most people think of gravity as just pulling on objects with mass, but Einstein showed it does something else. It warps the fabric of space itself. Imagine a trampoline stretched out flat. Put a bowling ball in the middle and it creates a dip. Now imagine light is like a marble rolling across that trampoline. When the marble gets near the bowling ball, the dip makes it change direction. Space works the same way. Any object with mass creates a dip in space and time. When light from a distant star travels past that object, the light bends. The more massive the object, the more the light bends. When a wandering planet passes almost directly between Earth and some faraway background star, the planet's gravity acts like a magnifying glass. It bends starlight from that background star toward us. For a short time, that distant star appears brighter. This brightness boost is called a microlensing event. The duration of the brightening tells you about the mass. For a Jupiter-sized planet, this brightening lasts about 1 or 2 days. For an Earth-sized planet, only a few hours. The smallest rogue planet ever detected created a microlensing event lasting just about 40 minutes. Scientists had to be watching that exact star at that exact moment or they would have missed it. Finding rogue planets this way is incredibly hard. You need to monitor millions of stars constantly, 24 hours a day, waiting for one of them to suddenly brighten. You are basically staring at the sky hoping to catch a flicker that might last less than an hour. When you detect a microlensing event, you can measure two things: how bright the star got and how long the brightening lasted. From those two measurements, you can calculate some properties of the object that caused the lensing. But here's the problem: the exact same microlensing signal could be caused by different combinations of mass and distance. A small planet nearby creates the same brightness curve as a big planet far away. Without knowing one, you cannot figure out the other. This problem is called the mass-distance degeneracy. Think of it like being told that x times y times 12. That could be 3 times 4 or 2 times 6 or 1 times 12. There are infinite possibilities and no way to know which is correct. For 30 years, every single time astronomers found a rogue planet through microlensing, they could only make rough estimates with huge error bars. They would publish papers saying things like, "This planet weighs somewhere between 10 and 100 Earth masses, and it is probably located between 3,000 and 8,000 light-years away." Imagine trying to study something when your measurements have that much uncertainty. You might be looking at something the size of Earth or something the size of Saturn. It could be in our cosmic backyard or halfway across the galaxy. Multiple teams tried observing the same event from widely separated telescopes on Earth. It did help a little, but still not enough. What scientists really needed was to observe the same microlensing event from two locations separated by millions of kilometers, one on Earth and one in space. The time difference between when each location sees the peak brightness would reveal the true distance through triangulation, but coordinating this was nearly impossible. Space telescopes are expensive and have packed schedules. You cannot just point them at random stars hoping to catch a microlensing event. The odds are terrible. But on May 3, 2024, three separate telescope networks detected a microlensing event happening near the center of the Milky Way. This region is called the galactic bulge, and it is the best place to hunt for microlensing because there are millions of background stars packed together. More stars means more chances to catch an event. The Korea Microlensing Telescope Network caught it first. This network operates three identical telescopes positioned on three different continents. As Earth rotates and one telescope loses sight of the target, another one picks it up. So, there's 24-hour coverage. Then, the optical gravitational lensing experiment spotted the same event. This project has been operating since 1992, making it one of the longest-running microlensing surveys in history. Both networks immediately recognized this as a potential planetary mass lensing event based on the duration and shape of the brightness curve. So, they started monitoring it intensively, but the actual breakthrough came from a pretty unexpected source, the European Space Agency's Gaia satellite. Gaia sits in a special spot in space about 1.5 million kilometers from Earth called the L2 Lagrange point. At this location, the gravitational pulls of the Earth and Sun balance out, allowing the satellite to stay in a stable position without using much fuel. Gaia's primary mission is to create the most detailed three-dimensional map of the Milky Way ever made. It measures the positions, distances, and motions of over 1 billion stars. The satellite is not specifically hunting for microlensing events, it just scans the entire sky repeatedly. But on that day in May, Gaia happened to scan that exact background star while the microlensing event was happening. Pure luck. Gaia recorded the peak brightness about 2 hours later than the ground-based telescopes saw it. 2 hours might not sound like much, but when you are separated by millions of kilometers and observing the same event, that time difference is everything. Think about how your brain perceives depth. Your left eye and right eye are separated by only a few centimeters, but that tiny separation allows you to judge distances. The same principle works with telescopes, except instead of centimeters, there's millions of kilometers of separation. By measuring the exact time difference between when Gaia saw the peak and when Earth-based telescopes saw the peak, astronomers could triangulate the precise distance to the rogue planet. This measuring tactic is called parallax. And once they had the distance, calculating the mass became simple math. I'm not going to get too much into how exactly they do the math here because I'm probably getting too scientific, but let me know in the comments if you want me to go deep on that. So, we have a planet 9,150 light-years away and 70 times the mass of our planet. This is the first time in history scientists have directly measured both values for a free-floating planet with this level of precision. The mass measurement itself reveals something fascinating. 70 Earth masses puts this planet right in what scientists call the Einstein desert. When astronomers plot all the free-floating objects they have found by mass, there is a clear pattern. Lots of small ones around Earth mass and lots of big ones around several Jupiter masses, but very few in between. This mysterious gap sits roughly between 10 and 100 Earth masses. The reason for this gap is not totally clear. It could be a detection bias, or it could be a real gap, meaning something about how planets form or get ejected makes this mass range genuinely rare. Finding a 70 Earth mass rogue planet right in the middle of this desert gives scientists a rare data point to study. But more importantly, this mass tells us something about where this planet came from. There are two ways to make a rogue planet. The first is ejection, the second is in situ formation. which just means it formed by itself without ever having a star. When a solar system forms, you start with a disk of gas and dust swirling around a young star. Clumps of material stick together, growing until you have planets. But early on, those planets are not in stable orbits yet. They interact with each other gravitationally. Whenever you have three or more objects pulling on each other, the math becomes chaotic. Sometimes planets swing too close to each other and their gravitational interactions fling one of them out of the system entirely. Computer simulations show the lightest planet almost always gets thrown out. Simulations suggest about 17.5% of Sun-like stars eject at least one planet. However, the average mass of an ejected planet is around 0.8 Earth masses, so if ejection typically throws out lightweight planets, how did this 70 Earth mass giant end up wandering alone? Ejecting something this heavy requires extremely violent conditions. You probably need multiple Jupiter-sized planets in the same system interacting chaotically, or maybe a passing star came close enough to disrupt the entire system. The second pathway is in situ formation. Gas clouds can collapse under their own gravity. If the cloud is massive enough, it becomes a star. If it's smaller, a brown dwarf. And if it's even smaller, it can collapse into a planetary mass object that never had a sun. For this newly discovered rogue planet, most astronomers still think ejection is the most likely explanation. Objects this size really benefit from forming in a protoplanetary disk where there is lots of material to accrete. They probably do not just pop into existence from a random gas cloud. Which means at some point in its history, probably billions of years ago, this gas giant was part of a planetary system. It orbited a star and had siblings, and then gravitational chaos threw it into the void forever. The observation itself was absurdly lucky. Gaia caught it during the 16 hours of peak brightness and recorded 6 data points. One day earlier or later, it would have missed everything. This proves that combining ground telescopes with space observations can solve the distance problem. Now that scientists can finally measure these wandering worlds precisely, the next big question is, how many are actually out there? The numbers are absolutely wild. Current best estimates suggest there are about 20 rogue planets for every star in the Milky Way. If we take a conservative estimate of 200 billion stars, we get 4 trillion wandering worlds just in our galaxy alone. 4 trillion planets drifting through space with no sun, no light, and no warmth, just traveling in frozen darkness for billions of years. Some estimates go even higher. There might actually be more rogue planets in our galaxy than there are stars. The galaxy could be swarming with dark frozen worlds that we cannot see. If these estimates are anywhere close to accurate, it fundamentally changes how we think about planetary systems and the universe itself. If you watched to the end, please click the like button and let me know your thoughts in the comments. God bless you and have a great day.